Now is it 12:30? The problem is my watch is like a little fast, so I sync them like all true spies do. And my watch invariably fails me.
Now it's 12:30.
Good afternoon. Welcome back to Chem 400. My name is still Bill Miller. Still going to try and do my best to teach you. This is approximately where we left off, and if I believe correct, where we left off was we had done a couple examples of these. We'd filled in all the prefixes here. Yes, good. So those are prefixes, and I believe I said this last time, but hopefully I'm saying it again, that you will have to know for your first exam. Your first exam includes a nomenclature portion that it's either 24 or 32 points, and it's a significant portion of your exam 1. 15 points for your nomenclature quiz this week. One approach to getting all the points you need for the grade that you desire is to be really good at memorizing and learn all your nomenclature. A nomenclature point is the same as a solve a problem point on an exam. Taryn?
Quiz is today, right?
Quiz is in your 2-hour portion of lab. So I believe yours is Wednesday. Yes?
Yes.
Yes.
Yes,
At 2
actually,
p.m.
days.
No quizzes. Now, of course, your quiz will be different than the quiz that they took today, but that's one of the reasons that I give you the format for the quiz, so that there's no there's no possibility that crosstalk between lab sections will help you, because you know as much as the people on Wednesday. There was a practice quiz on the Chem 400 website for everyone. So anyway, just another behind-the-scenes thing to keep it all hopefully as fair, equal, and equitable as possible. Any other questions before we keep going? Okay. So the one that I said was different was this prefix for half. That's only used for hydrates. Hydrates in particular. So I've got a slide here with 2 different hydrates on it. Calcium sulfate, sulfate.2H2O. We've actually solved some hydrate problems on the homework already and on the discussion. But the format goes like this. There's a dot, which signifies how many water molecules are associated with calcium sulfate in the solid phase. Hydrates will be solid. And as you've seen in the homework problems, if you take and you heat a hydrated compound, you can actually drive off some or all of the hydrated water molecules. And in the homework problems, you usually drive off all of them. But here we've only driven off some of them. As far as naming goes, this will be calcium sulfate dihydrate. Anybody cannot see that? Again, because I'm trying a new pen today, and it's tinier, but mighty, as they say. And for nomenclature, in this nomenclature, there's almost always a hydrate on the first exam, as you'll see from my old exams. Calcium is one word, sulfate is another word, dihydrate is the third word, and the di comes from the 2. Hydrate is always the word for the water, or the H2O in this case. We add heat, we remove some of the H2Os, we get left with calcium sulfate hemihydrate. Calcium sulfate hemihydrate, and nomenclature portions of this class are the only times when spelling counts. Otherwise, as long as I can tell what you're referring to, I'm happy. And spelling, not only, but also spacing, so you'd want to make sure that that's And I've got some pictures of the different hydrates here and some of their structures. What do you have to know for the exam? You have to know that hydrates exist, that if you heat them, it drives off the waters, and you have to know how to name them. Okay? Any questions about that? Yes, in this one, only some of the waters are evaporated. What you can imagine is that depending upon what temperature you actually use, you can drive some or all of them off.
So the temperature, not the composition.
The amount of waters, or I mean, I guess you could say the temperature or the amount of heat that you add.
Yeah.
And in one of the, so for now, heat and temperature are pretty much indistinguishable, although when we get to chapter 6, thermochemistry, we'll talk more about.
And then correct to assume that eventually all of it can potentially evaporate.
Yes, if you heat it, let's say this, I'm not sure about each specific case, but in practice, in general, yes, if you heat it at a higher temperature, if you add more heat, you could drive even this last half a hydrogen, half of a hydrate. And in fact, if your question, another question would be, what does half an H2O mean? It means that there's actually one H2O for every 2 calcium sulfates. And another thing we're going to see, so as part of the chemistry is an onion, it has layers, is that when we balanced reactions in Chem 300, when we went through balancing reactions now, we always had whole numbers for all of our coefficients. Once we get to future chapters, we will see fractional coefficients because we'll always be dealing with mole-sized quantities. And it is true, you cannot have half a molecule or half an atom, but you can have half a mole. Okay. So, Alicia, any more questions? Good questions. Good. Yeah. Okay, unfortunately, there is another set of number prefixes. A lot of them are similar, but as we talk about organic compounds, these are compounds that generally compose of CH, O, and N, carbon, hydrogen, oxygen, nitrogen, sometimes sulfur and phosphorus. They are the compounds that make up us, more or less. And, but it'll turn out that there are a typical number of bonds for these. Carbon typically has 4 bonds. Hydrogen has 1. Thank you. What about oxygen?
2.
Typically 2. Nitrogen typically 3. What we will see in this class, and I said typically for all of them, but 99.9% of the time, carbon will have 4 bonds. If carbon does not have 4 bonds, you ask questions about it. It'll be a weird example. So we'll say 99.9% of the time. That's also true for hydrogen. But for oxygen and nitrogen, we'll actually see different examples where sometimes oxygen has 3 bonds, sometimes nitrogen has 4 bonds. The example that comes to mind for nitrogen would be ammonium, in which case, sorry, here we go, that's ammonium. Big difference between NH4 and NH4+. NH4+ exists, NH4, not so much. That loss of an electron makes a big difference. Anyway, I know we're not at Lewis structures yet, but to show you an example of nitrogen with 4 bonds, there it is. So I will write typically here and typically there. One of the things I've said about Chem 400 is we're trying to show you rules that work 90+% of the time. So true in general for oxygen and nitrogen, but even then we want to be clear about when those cases are. So I'll write typically here. But typically means there are enough exceptions that we're nowhere near 99.9%. All right, now base names by number of carbons. 1 carbon, and this is, let me be specific, number of carbons in the longest carbon chain. And we'll say more about what that means, but for now, we do want to add that. For 1 carbon, that's going to be meth. 2 carbons, F, ETH. 3 carbons, prop. 4 carbons, bute. 5 carbons, pent. And from 5 carbons on, they're all the same. It's only the first 4 carbons that are different. That means for 6, 7, 8, 9, 10, hexa, hepta, octa, nona, and deca. Those are the same ones we put in the previous one. Well, I guess technically I should have A's here, but we'll talk about that too. We'll just put hex, hept, oct, known. Then we'll see that, well, I mean, anyway. I'm conflicted because technically they're like this with A's, but we're going to talk about what happens to that A shortly anyway. So I guess either way is fine.
Parentheses?
Let me just keep them the same.
Parentheses around the A?
Tell you what, come back to it after we do the next couple slides, and we'll see how we feel. Well, if these are the prefixes, then we also have to learn the suffixes. The suffixes are going to tell you about the bonding in these organic compounds. And so you can see the A here will be the A on the previous slide, but we're going to change it for the other ones. Let me tell you what these mean. For ANE, the ANE ending means that all the carbon-carbon bonds are single bonds. So I'll just write single, only single carbon-carbon bonds. It's a little weird with so many C's and parentheses, because the parentheses look like C's as well. But that's a picture of a carbon-carbon single bond. ENE has at least one carbon-carbon double bond. And that'll be 2 dashes, where each dash is a bond, and YN. At least one carbon-carbon triple bond. And question yet?
May or may not be a related question. Does this correlate with stability of the molecule?
So does this, meaning the number of carbon-carbon bonds between the 2 carbons, correlate with stability of the molecule? So the short answer is yes, absolutely. The long answer is called Chapter 9. Right, good question. I will not answer it because we will answer it later. It's a good, it's right on. Alcohols, and we'll do, well, let me do a couple of examples here. So, five carbons. 5 carbons is going to be pent or penta. Now, how many bonds did we say each carbon likes?
4.
4. And for organic molecules, if there's nothing else, you fill everything else in with hydrogens. Each of those hydrogens has 1 bond. This end carbon has 1 bond so far, so I will now add 3 hydrogens. The other carbon on the other end, same thing, needs 3 hydrogens. How many hydrogens do each of the carbons in the middle need? 2. Oh, and one more at the end. Doesn't even look right if it doesn't have it. And by the end of the class, you'll be able to look at Lewis structures like this, and they won't look right if you're like, ooh, that carbon only has 3 bonds. Something's up. And then, of course, you'll probably draw it 4. Now, this is pent for 5 carbons. Only single carbon-carbon bond, so this is pentane. Now, there are a couple different ways we've talked about pentane as far as structures. You can call it CH3. Put down 3 of those CH2s in the middle and then another CH3, and that helps you to think of the structure that we just drew. Other abbreviations for this? And I believe this is the one that's on the common molecular compounds list. And then, of course, you can just count up all the carbons, count up all the hydrogens, and you end up with C5H12. Those are all ways of referring to pentane. And of course, the more ways you have to refer to it, well, the more you care, the more interesting it is to us. Alcohols include the hydroxyl group. Here's where we differentiate hydroxyl from hydroxide. Hydroxide, is that an ion? It is. It's the hydroxide ion. Let's just start over here. That is the hydroxide ion. And as we talk about in the discussion section this week, there is a big difference between an ion and ionic compounds and covalent compounds. That is an alcohol with OH covalently bonded. I still have to fill in some hydrogens. As we'll see later on, also part of Chapter 9, when you have 2 bonds for oxygen, it's because oxygen also has 2 lone pairs for a total of 8 or an octet of electrons. Hydroxide would be in a compound like sodium hydroxide. Here we have, well, 4 carbons, bute. All the carbons are connected by carbon-carbon single bonds. Oh. And there's an alcohol group, so it becomes butanol with an OL ending instead of an E. And not in Chemistry 400 will you get the full understanding and be asked on tests to bring these back. Like when you get to OChem, they'll say, butanol, draw me the structure, right? All we're giving you now is we want to expose you to some of the different endings, and so you have to know bute means 4 carbons, single bonds, and that there's an OH group in it somewhere. Any questions about that? One more example. I'll fill in the hydrogens in a minute. Hydrogens, get tired of putting all those hydrogens in there, but they are there. Now, how many carbons do we have in our longest carbon chain here? 4. Think of the chain as the longest continuation, even though it goes through the double bond. We're up to 7 carbons. That means we're on hept. We have 1 carbon-carbon double bond. This will not be heptane, this will be heptene. heptene, and that was why I hesitated to put that A in there, because the A disappears and becomes heptene. There's actually more to do for naming for this, and I have to, I'm sorry. I have to put in all the H's. It doesn't look right without it. Whoa. 1, 2, 3, 4, 5. I don't think that needs 2 H's. Just 1 H. Good, because I wrote heptene down there. Now, what do you have to know about this? Well, let's see. You have to be able, so key things here, you have to be able to recognize the difference between an OH group and a hydroxide group. And you have to tell me that when you see the ENE ending, it means there's a double bond, and the YNE ending, it means there's a triple bond, as well as ANE. Okay. And we're not going to have to do this for a while, but I'll point out that this is a CH group. So we have CH3, CH2, CH, CH. And I'm going to write this version down here. And the number of hydrogens is a clue as to what kind of bonding is going on. Any questions about that, Alicia?
Sorry, the difference between hydroxide and what? The test.
Oh, yes, you do have to know the difference between a hydroxide and an alcohol, or also called a hydroxyl group. You need to know your number of prefixes, and you have to know what, so if I say butane versus butene versus butyne, what kind of carbon-carbon bonds are there?
Memorize pages 112 and 13.
Pretty much. A couple other ones. One we've run into already, briefly. In my previous lecture, that is the COOH group. It is for an organic acid. It is also called a carboxylic acid. The COOH group always looks like this. C with a double bond to an O and a single bond to an OH. The carbon in a COOH group already has 4 bonds. The oxygen has 2 bonds, so it will have 2 lone pairs. The oxygen down here has 2 bonds. It will also have 2 lone pairs. For now, it doesn't matter where you draw them, as long as you draw them around the O somewhere. With this skinny dry erase marker, I really do feel like I've just made the jump from kindergarten into 1st grade, and I'm like, ah. But I'm doing my best here. Feels too small. Memorize this. This shows up in most lectures for, or I don't know, like 50% of the lectures is the COH group. And when you come back to it in chapter 11, you will remember it, for sure. And all the intervening chapters. This one, by the way, you don't have to know how to name this, but it would be called butanoic acid. But for 4 carbons, and for all of them are connected by single bonds. Oic acid for the fact that it's a carboxylic acid. Next group, NH2, that's an amine group. Those will be weak bases. The one amine that you have to know for sure for exams is NH3. NH3 is ammonia. What's the name of NH4 plus? Ammonium. We talked about this a little this morning in discussion. We'll talk about it more. We are very interested in distinguishing ionic compounds from molecular compounds. We are very interested in distinguishing ionic compounds from molecular compounds, even if they look very similar. And so that's what we want to be able to do. So I'm going to put, ionic and ammonium. Now here's a formula for another amine. And it has an NH2 group. Now, what do you have to know about amines? Well, as I said, you have to know ammonia. That's it. You have to know that ammonia is a weak base. Now, as far as NH2 groups, we'll see them again in future chapters, but that's sort of a heads up for future chapters. Good. Now, this is a typical question that you could see on your exam, and the question could be, tell me what you know about this molecule. You would tell me it has, in its longest carbon chain, 6 carbons. Tell me what you know about hexenol. Longest carbon chain has 6 carbons. There's at least one carbon-carbon double bond. And I'll use the abbreviation C double bond C there, at least one C double bond C. And also an alcohol group. Alicia, do you have a question?
Are you finding that there may be more than one carbon chain?
Oh, so the hex means 6 carbons. And let me just, so this is not on the exam, this is just to answer a question, and I've noticed this too, but let's say this is our longest carbon chain. There is a difference between this and that we don't care about right now because it's more complicated than we will talk about, but without that side chain, this is hexane. With this side chain, it's called methylhexane because there's a 1 carbon side group. So this would be the longest carbon chain. All right, we haven't got as complicated as allowing side groups yet. We're thinking about them, but we will. And in fact, one of the things you'll see, this is in your textbook actually, in chapter 3, it talks about organic groups. We're following on pretty well. We actually spend a lot more time on this type of stuff than your textbook does later in the course. And that's because I think this stuff is so useful, practically speaking.
And you're not going to see stuff like C, 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 then O, and then C, 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 U. That's not going to happen.
Like that?
Yeah, chains connected by something.
So what I will say about this is, as far as thinking about nomenclature like this, no. But I can ask you to draw a Lewis structure like this later in class.
Okay.
Yeah, good question. Then we get a name like this, 2-amino-pentanoic acid. Do you see that word amine? What would you guess is in there? Somewhere there's an NH2 group. Contains NH2. That dash right there is the bonds to the rest of the molecule. Like right here, like right there. 5 carbons in longest chain, connected by single bonds, pentanoic. And it has a dash COOH group because, well, I don't think I could put this part on the test, but it is true. So I put this in parentheses. I wouldn't give you this name and expect you to spit out my COH. Last but not least, I see a triple bond here. What do you think part of the word will be for the name of this? YNE. It'll have YNE. Or that group in there somewhere. And it has an alcohol group. So that kind of identification, generally speaking, is what we're talking about. Any questions about that? Okay. If not, I believe that is the last slide in this one. Give me a minute while I pull up the next lecture. Let me see. There we go. Lecture 3, Chapter 4, all about solutions. We gave a couple of definitions here. We will cover Chapter 4 in its entirety in gory detail. Let me grab my notes. So as far as solutions go, we'll start with 4 pieces of solution terminology. First off, a solution is a homogeneous mixture of 2 or more materials. Homogeneous means that basically, so functionally, a homogeneous mixture will mean it looks just like water. There's no pieces in it. Whatever is in it is dissolved. You can think of salt water. You can think of 1 molar HCl. 1 molar HCl is an acid. It looks just like water, though, until you spill it on your skin. So they're homogeneous. That means no chunks in it, seamless. Solute, the component of a solution present in the greatest amount. Wait, that's wrong, isn't it? Sorry, solute. I apologize for this. I'm sorry. So, solvent. Solute, there we go. I apologize. The component of solution present in the greatest amount. That is the solvent. Does that sound better? Hopefully. Solute, any component of a solution present in a smaller amount. A dilute solution is a solution with low concentration of solute. A concentrated solution is a solution with high concentration of solutes. Yes. Now, concentration is a quantitative measure. Quantitative, the word quantitative means with numbers. Qualitative means without real numbers, just observational. Quantitative, with numbers, measure of an amount of solute in a given amount of solvent. The units we will use, one of the main set of units is molarity. Molarity is represented by a capital M in this class. I want to make sure that we know, so we have capital M, that's for molarity. MOL, that's moles. And then whenever we want to talk about molecules, we write out the entire word. That would help me a lot. Hopefully that might help you a lot as well, because we do want to distinguish between these three things. And we will see that and really from this point onward, we very rarely talk about molecules. We talk about moles a lot, and we talk about molarity quite a bit. Process, weigh out 58.44 grams of sodium chloride. That's exactly 1 mole. We can make a 1 molar solution by then dissolving that in water in a volumetric flask. These are volumetric flasks, you can tell by the shape. We will use volumetric flasks as early as those of you who have lab today to make your solutions. We will use, this looks like a 1 liter, we will use 100 milliliters. But we'll do the same process. We'll pour in salt through a funnel. We'll pour in some water. We'll dissolve the salt. And then we will fill up to the line. We'll set the meniscus right on, the bottom of the meniscus right on that line. We will have a a specific concentration solution. Good? Find the molarity of a solution that has 25.5 grams of potassium bromide, KBr, dissolved in 1.75 liters of solution. Now, whenever I solve molarity problems, I like to write them out like this. Blank molarity KBr equals blank moles of KBr over blank liters of solution. And I would say, even if sometimes I do write this out, even if I don't write it out, it's what I'm thinking about when I make it. So in this particular problem, I know my liters of solution, I can plug that in right away. I don't have my moles of potassium bromide, but I have my grams. So many times we turn grams into moles. Using the molar mass, if I look it up, I get 119.00 grams of potassium bromide per 1 mole. Divide that out, I get 0.214 moles. Plug that back in. And solve, I get 0.122 molar, where molar is the abbreviation or the cutesy nickname for molarity. 0.122 molar potassium bromide. That's the English pronunciation. Molarity works as well, but molar seems easier to say. Any questions about this top problem? What is the molarity of a solution containing 3.4 grams? This is going to be a companion problem. Please work it. And the answer key is already posted on the Chem 400 website. Number 4, how many liters of 0.125 molar sodium hydroxide contain 4.56 grams of sodium hydroxide? I'm going to set it up in exactly the same way. Again, I've been given grams of sodium hydroxide, which I can convert into moles. Using the molar mass, in this particular case, 40.00 grams. I get 0.114. And you can fill it in with an X. That's what I'll do in this case, since I got to cross multiply. And when you solve for X, I get 0.912 liters. A word about units. So my units here for liters, I could write liters of solution as well. Now, when I talk about molarity, molarity is always of a solute. So whenever you have a capital M for molarity, you will always have what is the solute, what is dissolved in that molecule. So 0.122, I guess I should add that. 0.122 molar potassium bromide. That is a complete answer. Another companion problem. Let me just check in. Any questions about what I've got up on the board here? How many people have worked similar calculations in their Chem 300 class? How many people have not ever worked calculations like this? Or don't really remember them? Well, they're what I like to call bread and butter calculations, meaning that they underlie a lot of what we're going to be doing for the rest of the course. And so if in Chem 300 and in this class too, we do 100 different molar mass calculations to turn the grams into moles, we'll do probably 100 different calculations to turn using molarity as well. We'll do probably 25 or 30 different dilution calculations. Dilution is adding water to a more concentrated solution. That's all it is. Quantitatively, the dilution formula, M1V1 equals M2V2, where M's, the capital M's, are molarities, and the V's are volumes. A more general form has C for concentration. I typically use the M1V1 equals M2V2 only because we're almost always dealing with molarities in this class. Here's a picture of how this works. So measure a certain volume of solution, then add water to it. Key for this, and one of the things I've said is that Chem 400 is at least partially a reading class. And when you read, the word you're looking for is some version of dilution or diluted, and that will tell you to use this formula. When diluting, concentration decreases, but what about the total number of moles of solute? The total moles of solute stays the same. Thank you, Alicia. And this runs through a calculation that shows that the moles in the concentrated solution equals the moles in the dilute solution. I'm going to write that out. My abbreviation for solution is SOL''N. Have I used that already? I don't know. But I use it a lot. And I square that off because that's a common mistake in thinking about how these solutions work. Well, this is lovely. What is the concentration of a solution prepared by diluting 45 milliliters of 8.25 molar nitric acid to 135 milliliters? Look, I've already got my equation right here. I guess I could use either one, actually. Tell me, when you're reading a problem and you encounter the word of, what does it mean? Say this was a math class. Subtract, multiply, divide. I've heard different answers. Which do we think it is? Multiply. Of means multiply. There you go. Almost always the case. I can't think of an exception, actually. Well, when it's surrounded by numbers, and especially one of the keys to solving Chem 400 as a problem in and of itself is whenever you see of between two different numbers, you're going to be multiplying them together. Another thing about the dilution formula, it works when you multiply using both sides with the same sets of units. That means if you have two sets of milliliters, you can work this in milliliters. If you have two sets of liters, that works as well. Whatever the units are, as long as they're the same. I'm going to work this problem in milliliters. I know, let's see. Well, it says diluting 45 milliliters of 8.25 molar nitric acid. That's going to be my concentrated. .45 milliliters, well, so let's start with this, 8.25 molar. 45.0 milliliters. My M2 will be my unknown, and my V2, 135.0. That's what I mean. So you can see these two numbers on either side of the of are multiplied together. M2. Does M2 have to be bigger or smaller than M1? Has to be smaller. Please check that. I know you know it, but sometimes on the exam, you get going quickly, so it always helps to look at and I get 2.75 molarity HNO. That's what I mean by proper units on a molarity. It always tells you what is the solute right there. Here, we're going to do this. We're going to do this one. It says, how would you prepare 200 milliliters of 0.25 molar sodium chloride solution from a 2.0 molar solution. Here we know that this number is our more concentrated, so this one's going to be M1. We have these two numbers with an of between them. These are going to be our M2, V2. And I've said this to a couple people. I want to make sure I tell the whole class. By the time, when you do your homework and when you get to the exam, feel free to bring highlighters to make whatever annotations you want on your exam, on your homework, that will help you understand it. Filling everything in. I don't have my V1, but I have everything else. Solving for V1, I get 25.0 milliliters. And I'm going to actually answer, how would you prepare it? Well, we would, or I would, I guess. How would you? I would pipette 25.0 milliliters. Of 2.0 molar sodium chloride solution into a 200 milliliter volumetric flask. No trick. Then fill the volumetric flask until the bottom of the meniscus was sitting on the line. Then fill the volumetric flask until the bottom of the meniscus was sitting on the line. Invert for 2 minutes to mix. And I'm going to write that last part up here. Invert for 2 minutes to mix. And we'll make some solutions. We won't necessarily dilute things in lab number 2. We'll be making them from grams of sodium chloride, but it's good technique to learn. And what we're learning here, by the way, is that when we measure out volumes, we tend to use pipettes. Graduated cylinder is not quite as accurate, sometimes accurate enough. We never measure volumes for reactions or solutions using a beaker. That's the take-home message of lab number 1. Any questions about this? Solution stoichiometry. What volume of 0.15 molar potassium chloride is required to completely react with 0.150 liters of 0.175 molar lead to nitrate? Well, this is going to be my diagram of how to solve this problem. I'm going to start with my given volume of thing A, which will be lead 2 nitrate in this case. I have 0.150 liters. I know that there's an of there, so chances are I'm going to be multiplying these two numbers together. My molarity is my conversion factor. I know that molarity is moles per liter. I want liters on the bottom, so I'm going to put moles on top. 0.175 moles of lead-2 nitrate. Molarity is my unit conversion factor. And sure enough, these two numbers are being multiplied together. I've been given a balanced reaction. I'm starting with my lead-2 nitrate. I'm being asked about my potassium chloride. The next step is going to be a mole-to-mole ratio from the balanced reaction that tells you how they react. I have to have moles of lead-2 nitrate on the bottom, moles of potassium chloride on top. My line wiggled a little bit, or sort of sang. There's my mole-to-mole ratio. Now I have, let's see, my liters of solution have canceled. My moles of lead-2 nitrate units have canceled. I have moles of potassium chloride. And I have the molarity of my potassium chloride. This time my molarity will be upside down. I'll put 0.150 moles of potassium chloride. And then I get liters of potassium chloride solution for my units. That's what I mean here. You start with your volume. You turn that into an amount of moles. Turn that into an amount of moles of something else. And then use your molarity to get back. So let me see. My unit conversion factor here will be molarity. Then mole-to-mole conversion. Chemistry is like an onion, and all of these calculations are just like this. Molarity, mole-to-mole conversion, molarity. Just like in Chem 300, you started with grams, use molar methods. When you do this, you should get 0.350 liters. And in fact, you can also write liters of potassium chloride solution. Any questions? Okay. If not, then we'll move it on. Do you see this red 2? Is it in your lecture notes?
Yep.
Oh, good. This is a companion problem. This problem we're definitely doing. It says the following reaction is used to prepare hydrogen gas. Magnesium solid reacts with hydrochloric acid to make magnesium chloride plus hydrogen. What mass of hydrogen gas can be produced from 2.00 grams of solid magnesium when that's put into 100 milliliters of 0.100 molar HCl? This is actually what we do in lab number 4. Very similar to it. First question for you, do I have enough information to find moles of both of my reactants? Do we have enough information to find, well, let's say this, using molar masses and things like that?
Yes.
Yes, we do. Next question, is this a limiting reactant problem?
Yes.
Yes, it is. That's how you read this. I have enough information to find the moles of each of these going to be limiting reactant. And what's going to happen is, well, for solids, we give you grams. For solutions, we give you volume and molarity. Now we're in chapter 4. In chapter 5, we're going to use the ideal gas law to figure out moles of gases. So we're just getting more and more ways to tell you how many moles of a substance we have. So if it's a limiting reactant, you're going to have to do both of them and find the smaller amount of hydrogen. Still, that's the same. We have 2.00 grams of magnesium. We know that the molar mass of magnesium, at least to 4 sig figs, 24.31 grams. We know that there's a 1-to-1 mole ratio. This is a balanced reaction. And we know the molar mass of hydrogen. One thing is I've mentioned to a couple people, and I'll mention it now for everybody. Now that we are in chapter 4 and for the rest of the course, pretty much the only molar masses you use in any problem is the molar masses of the formulas in the balanced reaction. (100 milliliters). Molarity is moles per liter. I'm going to convert 100 milliliters into liters by moving the decimal point 3 places. That means that 100 milliliters is 0.1000 liters. Please be careful. I encourage you to learn to do this in your head, but if you move the decimal point the wrong way, it does have a big effect on your answer. Now so that is 100 milliliters changed to liters. I also have 0.100 molar HCl. I convert that into moles per liter, sort of unpacking what molarity means. And this time, for every 2 moles of HCl, I get 1 mole of hydrogen. And so there we have a complete setup for solving this problem. When we solve this, what we find is that we get for the magnesium, we could make 0.166 grams of hydrogen. For the solution of HCl, we get 0.0101 grams of H2. That's a 0. So how much hydrogen can we make? It's always the smaller amount. What mass of hydrogen gas can be produced? This mass. This mass is the smaller amount. We'll actually do this in lab. Lab 4, when we do it in lab, we'll start with the teeniest, tiniest piece of magnesium. And magnesium will be our limiting reactant. We will make it so. And that's one of the questions for lab number 4, is to prove that. Turns out that in solids, the atoms are very tightly packed. So even a small mass gives you a lot of atoms. Any questions about this? If not, then we'll continue and talk about electrolytes. We're now on section 4.5, electrolyte and non-electrolyte solutions. Does this picture show up in your lecture notes? Good. And this is the subject for this week's discussion section as well. When you pour salt into a solution with a circuit and a light bulb and a battery, what we find, table salt that is, table salt, what's the formula for table salt? NaCl. Table salt, sodium chloride, it conducts electricity. That's hence the term electrolyte. For sugar, it is a non-conductive. Non-conductive is non-electrolyte. And we want to talk about what happens when these cases occur. All right. Oh, I have a video for you. Oh, I have no sound for you though. Well, we'll have to pretend. Or maybe I have sound. Stop. Well. Sorry for the technical difficulties. Now you can see it. You know what? We're going to come back to this. I'll bring it next time with sound. Good. Now let's do our second reaction type. Do you remember what our first reaction type was? It was combustion. We said anything that's burned plus oxygen goes to carbon dioxide and H2O. Those were gases. We said that when it says reaction type, or that's a reaction that I can ask you to write on an exam, and especially on the homework. Dissolving reaction for sodium chloride solid. Take sodium chloride solid as the reactant. The species on the product side are aqueous. In this particular case, because sodium chloride, when it dissolves, becomes sodium plus and chloride minus, and those two are in the aqueous phase. Does anybody know what the aqueous phase means? Or a question? Question, Brenna? Do you know what it means? Yes.
So why does it dissolve, first of all, the hydrogen as like an NaCl solid plus H2O liquid? And then
Great question. Very common question, too. Where is water on the reactant side? That's sort of where you're getting at. The answer is that I'm about to draw you pictures of it, but we will show you where the water is, but the only place water appears in the reaction is in these phases. Okay? Yes. Does that answer your question? No. Let me draw my pictures. All right, so what does aqueous mean? Well, that means that the species that are aqueous have what's called a hydration shell. Sodium is positively charged. If that's my sodium ion and it's dissolved in water, I'll put my water over here. How many people are familiar with the fact, let me draw my dots actually. that water has a bent structure? Raise your hand. Good. Next question, not that I've taught this to you at all, but so glad that you know, and we will teach you too. Oxygen or hydrogen, which part of water is the partially negative part? Oxygen is the partially negative part. We show that with what's called a lowercase Greek letter delta. Delta means partial minus. So I've drawn a little delta minus there. Delta positive for the hydrogens. Don't worry, you don't have to know this yet. We will teach it to you, but that's why I want to show you right now. And that is my water molecule with partial charges. Assuming we're familiar with this, or now we can know this, which side of the water molecule is attracted to the sodium ion? Oxygen. Partial negative is attracted to positive. It will generally look like this. The specifics are not that important as long as the oxygen is closer to the sodium than the hydrogens are to the sodium. The exact number doesn't matter either. Something like that. Could be 4, could be 5, could be 6, doesn't matter to me. But this is a hydration shell. A hydration shell is the water molecules surrounding the sodium. Okay. What about if we do a chloride ion? Will the H or the O be attracted to it? The H. We will talk about this later, but it turns out that a chloride ion is bigger than a sodium ion, so that part I'm not making up. Nothing up my sleeve. Some combination of H's closer and O's farther apart, whether you've got both H's closer or just one, I don't know. In general, H's are closer. This is a schematic. This is a snapshot of what's happening. Of course, these water molecules are moving all the time. So, is this a real picture of what's going on? No. It's a picture that helps us understand what the aqueous phase means. Draw a couple more to complete my hydration shell. And again, the exact number doesn't matter, but if I ask you to draw a hydration shell in an exam, and you probably will see that I've asked at least once, the key thing to know is that you have the positive with the partial negatives closest to it. Now, let's talk about why dissolving happens. Because here, I have +1 attracted to -1. These are partial charges. It turns out if you get a whole bunch of partial negatives, it can overcome the negative charge for the chloride ion and make something dissolve. That's why we're drawing these pictures, and that's why hydration shells matter. A whole, or will be suitably vague, enough partial negative charges can allow the sodium to dissolve. Well, I think there's a better way to say that. Enough partial negatives.
To override the NaCl bond.
Can override the negative of the chloride in the NaCl. And I'm going to be specific here. I'm going to write -1 right there to separate it from the partial negatives, the full-on negative. We could also call partial negative charges namby-pamby negative charges. They're less than 1. the -1 charge of Cl- to break the sodium chloride ionic bond. That's why it dissolves. That's our picture of dissolving. Okay. Any questions about this? Yeah.
Is this where like the different types of bonds come into play, where like your hydrogen bond, your different types of?
It's a great question. So,
Yeah. Is that,
yes, intermolecular forces, hydrogen bonds, dipole-dipole forces like that. Absolutely. Right? And sort of the big picture, right, that we've already started to look at is, let's think just about what is ionic and what is covalent. And then later on, once we learn to draw Lewis structures, some of you probably know, some to many, then we will look at intermolecular forces such as hydrogen bonds, dipole-dipole forces, etc. And chapter 11 puts it all together. Yeah, so I would say hang in there.
Yeah.
This is all part of the story. Right? If Chem 400 is a novel, we are in chapter 4. If it were a textbook, it would be in chapter 14. But yes, it is, right? So, and what I would love is if you use the knowledge that you already have of chemistry and hydrogen bonds, it just sort of, yeah, you'll see memory jogs as you go, and it hopefully will help you fill in the picture. And hopefully you already know some of the picture too. So. Good. Let's see. It doesn't have to be solid here. We could have solid, liquid, gas dissolving reactions, and we'll see them. It does have to have aqueous products. So we will see. I could ask you to write a dissolving reaction for oxygen gas, O2. Anyway, we'll get there. Let's do, oh, this is sodium chloride. I think we have some more information about, yes. Sodium chloride is a strong electrolyte. When strong electrolytes dissolve, they break up 100% into ions. These ions conduct electricity in solution. Period. These ions conduct electricity in solution. And so the picture I gave of the light bulb lighting up, that is because literally, and I don't use that word lightly, literally ions are moving through the solution to carry the charge. All right, good. Sugar is a non-electrolyte. Let's start with this. Dissolving reaction for sugar. Sugar, table sugar at least. There's the chemical formula for table sugar. It's also called sucrose. Sugar is a non-electrolyte. I can ask you to write a dissolving reaction for sugar. It goes like this. The product's going to be aqueous. Because it's a non-electrolyte, it stays as one whole molecule. Whereas strong electrolytes, when they dissolve, they break 100% into ions. Sugar stays as whole molecules when it dissolves. Does it dissolve? Yes. I will now drink dissolved sugar in my coffee. But stays as whole molecules. Stays as whole molecules when it dissolves, comma, 0% ions. No ions, no conducting electricity, no lighting of the light bulb. So those pictures, when we compare sodium chloride and sugar, both are dissolving. Strong electrolytes dissolve, non-electrolytes dissolve. You get different numbers of ions. So non-electrolyte could also stand for non-ionized. Still dissolves. Any questions? These are the two endpoints. So you can't get more than 100%, you can't get less than 0%. You can get between. All right. Yes. Acetic acid is a weak electrolyte. There are only 3 types of electrolytes. All 3 types of electrolytes dissolve. To be any kind of electrolyte, you dissolve. Acetic acid is a weak electrolyte. Turns out that in its pure form at room temperature, acetic acid is a liquid. We can write a dissolving reaction for anything that's a liquid. It just means that whatever it is on the reactant side, and whatever happens on the product side, everything is aqueous. Well, weak electrolytes break into ions less than 5%. So it dissolves, breaks into less than 5% ions. Now this is where the reaction's going to get a little hinky, because I'm going to write everything on the product side will be aqueous, but I'm going to have to put percents under the numbers. So the first thing I'm going to write is this entire molecule in its aqueous phase. And it's going to be greater than 95%. I apologize. I will take. So stop me when I run over like this, please. Let me just finish this one thing since I've got it up here. You'll also have acetate ions. You'll also have hydrogen ions. These two will be less than 5%. And I'll stop there and I'll say more about it next time. I apologize for keeping you over. We'll pick up there next time.